All right, guys, so we're going to be talking about the behavior of gases. This comes from chapter 14 in our textbook. If you remember, chapter 13 was on liquids. In that chapter, we learned about behaviors like buoyancy and liquid pressure. Turns out that gases have similar properties, although the behaviors can be noticeably different from liquids. So this is the first of 3 videos I'm going to record on the topic. So we're going to start with the question. So imagine you're outside holding a balloon, and you release the balloon and watch it rise into the sky. As the balloon rises, the size of the balloon either increases, decreases, or remains constant. So take 10 seconds to think about this. Okay, so we're not going to answer this right now. We will answer it at the end of the video. By then, it should be pretty obvious what the answer should be if it's not something you know already. So before we get too far into this, I want to review some basic vocabulary. Remember that a fluid is a substance that flows. So this is anything that flows. So fluids have a couple of common properties. So first of all, they do not retain their shapes. They take whatever shape the container is that holds them. 2 primary examples are liquids and gases. So it's going to be important that you remember that both liquids and gases are fluids, so that a lot of the properties we learned about liquids you'll hopefully recognize as being similar properties for gases. We also need to define volume, just make sure we understand that. So it's the amount of space a substance occupies, pretty basic. And then mass density, which again is mass per volume, or mass divided by volume. So to make it easier, mass density is the only type of density we're going to be talking about, so I'll just call this density from now on. The density for a liquid has some significantly different behaviors than the density of gas. I just wanted to point those out. So for liquids, the density is pretty much constant. It's very difficult to change the volume of a liquid. So we're just say, for the most part, densities are constant. Gases are noticeably different, though. They are easily changed, easily compressed, so the density is relatively easy to change around. All right, so a couple of reviews of what these substances are at the molecular level. So we're going to focus on liquids and gases. So first of all, liquids here. What this picture is trying to show you is that compared to solids, liquids are loosely bound, where solids have these fixed bonds between them. The loose bonds give them the ability to flow, so why they're fluids. They're also, the picture is trying to show you that the spacing is closer than the typical spacing of a solid. That's important because that brings in the incompressibility of a liquid. It's very hard to compress, so that's part of the reason why we say the density of liquid is more or less constant, although that can change with temperature. Gases, on the other hand, the picture kind of looks similar for gases, but it's significantly different in terms of how the molecular behavior is. Gases are not bound at all, so they're free to kind of fly around, very little interaction. They're widely spaced, which is why they're so easily compressed. There's not a lot of interaction between the molecules for a gas. So if I bring up a picture like this is just a picture at high altitude. I want you to look at it for a minute and think of what it is you're seeing in this picture. All right, so a lot of people look at this and they see, well, it's haze. It's the haze caused by pollution, by human pollution. And that's not really what we're actually looking at here. If we go up even a little higher, you'll see that there's still that haziness above the Earth. So what I'm actually showing you here is the atmosphere. So anywhere you go above the Earth, you're going to see this atmosphere. Now in this picture, I really like it because look how blue it is. So as you know, the sky is blue. But if you compare it to space, space is quite black. So what gives the sky the blue, or the atmosphere this blue look, is the sunlight that's coming through the black of space. You can't quite see it. It hits our atmosphere, and when it hits our atmosphere, it scatters. So we're not really going to go into this principle much, but just other than the fact that the hazy color, especially the blue that you're seeing, is caused by the scattering of sunlight. Now it's important to notice that out here in the black, there's a lot of sunlight out there. So, more so than actually hitting our Earth, because it's spread out even more by the time it hits us. But we don't see it because there's no atmosphere to scatter the light. So that's why it looks black out here and kind of that hazy blue inside. So gravity is actually the main reason why we have an atmosphere to begin with. Just like when you try to jump, you always fall back down to the Earth because of gravity. It's the same thing for the atmosphere. So all those little tiny gas molecules are attracted to the Earth through gravity. And it's a good thing they are, because if they weren't, they would actually leave and just kind of drift off in space, and we'd have nothing to breathe. So another question for you. What is the atmosphere mostly made of? Okay, so a lot of people go with oxygen because they know that as human beings we need to breathe oxygen, and so it seems like that would be the primary component of our atmosphere, but it's actually not. If you look at this pie chart here, you'll see that nitrogen is the primary composition of Earth's atmosphere, which means that what you're breathing every day is mostly nitrogen. So oxygen is an important component, but a lot less than nitrogen. So percentage-wise, 78% of the air roughly is nitrogen, 21% is oxygen, and then you'll notice everything else, carbon dioxide, water vapor, all that is just 1% of the total composition of our atmosphere. So the other day I was looking at pictures of people climbing Mount Everest, and I thought it was interesting. I started noticing a trend between all the pictures. And if you notice right there, all of these climbers are wearing breathing masks. So some type of masks usually attached to an oxygen tank so that they can breathe at this altitude. Well, what's interesting is if you look at the background here, notice how they're not nearly high enough to see the black of space. And in all reality, in terms of the total height of our atmosphere, they're not all that high. They're relatively low. So if the atmosphere still goes up for many dozens of miles above this point, why do they need oxygen tanks to breathe? Well, the answer comes into the way the atmosphere is stacked if you go up vertically, or what we call altitude. Okay, so here's a graph that shows the composition of the atmosphere at certain altitudes. So if you notice, here's Mount Everest. So, and then this line right here is showing that about 5.6 kilometers above sea level, so you've already reached a point where 50% of the Earth's atmosphere is below that point. Okay, so when you're at the peak, when you're climbing up trying to get to these higher regions of Mount Everest, most of the atmosphere that we normally breathe is actually below you at that point. And since climbing is a very physically intense activity, you need more oxygen than is present at that point. So you have to have that extra help to get the oxygen you need at that point. Well, it's interesting because if you go up, keep going up here at 30 kilometers, which is roughly 20 miles for those of us who grew up in the United States. So at roughly 20 miles, 99% of the atmosphere is actually below that point. So the height of the atmosphere is kind of interesting. Where you cut off the top is a little bit arbitrary, because after 30 kilometers, you've pretty much reached the end of any significant amount of atmosphere. But notice the spacing here. So here we have a space of a little more than 10 kilometers, which again is about 6 miles. There's a difference of 9% in the atmosphere that's between those 2 points. But then if you go here, which is, let's go a little bit further, so a little more than 10 kilometers, there's a difference of 40%. And then here, the last little roughly 6 kilometers is a gap of 50%. So what you're seeing is the density of the atmosphere is not constant. It's much more dense at low altitudes than it is at high altitudes. So that gives us a lot better explanation for why, even though Mount Everest isn't all that high in terms of the total height of the atmosphere, it is quite high in terms of the density of the atmosphere. So you need those breathing masks. So if you think about this whole issue, then you should start to ask yourself, well, why is the density so different at higher altitudes? If you remember our discussion of liquid pressure, then this should actually become relatively obvious. So there's two key terms. So the idea of weight and compressibility. So if you take a column of air, like the one I've shown here, we tend to think of air as being this light, fluffy, kind of very easy to maneuver gas that has no noticeable weight. In reality, air has a lot of weight. We just don't notice it. So there is a lot of weight to air, and air as a gas is very compressible. All right, so if you remember liquid pressure, the idea was that the pressure at a certain level, so let's just say right there, is due to the weight of the liquid above you. Now, in a gas, it turns out that the idea is the same. So the air pressure or gas pressure is due to the weight of all the pressure above, the weight of all the gas above you. Okay. All right, so we're going to talk more about that here in a minute, but we're just going to come up with a key point, right? So the density of the atmosphere decreases with altitude. So you can either memorize this, or you can, if you just think about it, it's kind of common sense. There's more weight above you at lower altitude, so there's more density at lower altitude. Okay, so I want you to think about what other concept this affects. Well, I actually just talked about it. There could be multiple concepts, but the one that I was thinking of is air pressure, and so I brought that in earlier. Okay, so there's a connection between the density of the atmosphere and the pressure of the air at a certain altitude. So here another little graphic. So in this case, the column here you're trying to see is showing you the density. So just as we said, the air is much more dense at lower altitudes and much less dense at higher altitudes. Well, that also means that at higher altitude, there's a lot less weight of the combined air above any point, so there's a lower pressure. Where at the bottom, there's a lot of extra weight above you, so there's a lot of higher pressure. Okay, so our aviation students should know this quite well, right? They know that the higher you go, the less air pressure there is, so it changes how you fly, how you control that, and so this is a pretty known concept to them. But for the rest of us who don't spend much time at higher altitudes, this might be something that we don't really ever think about. All right, so let's go back to that original question of the balloon. Okay, so if I blow up a balloon just here at ground level in our classroom, okay, what I'm doing is I'm filling the balloon with air particles or molecules, right? So I guess if it's coming from me, it's mostly carbon dioxide molecules. But the point is that there's all these little molecules that are bouncing around like crazy inside the balloon. And when they do, they collide with the wall of the balloon. So I'm trying to kind of show you a picture of the collisions of the molecules. So every collision is going to apply a force to the outside of the balloon. So you think about all these little molecules bouncing around, hitting the outside of the balloon. Well, this is what we call the pressure inside the balloon. This is the cause of that pressure. So if I blow up the balloon more by just blowing more air into it, what I'm doing is I'm increasing the number of collisions, which increases the number of impacts, which increases the pressure. So the more air I blow into it, the bigger the volume of the balloon. Now, the other way to think of it, the reason why this became bigger is because I increased the pressure inside of the balloon, and there was more pressure inside than outside, which is why it grew. Okay, so let's go back. So if I only have a certain amount of pressure, it's going to reach an equilibrium where the outside is equal to the inside pressure, and the balloon volume is stable. When I blow more air into it, I increase the pressure inside. So now it's greater than the pressure outside, and it gets bigger. All right, so now let's go back to our balloon. So here's a balloon at ground level. Okay, I blow it up, and then I'm going to let it go, and I'm going to let it float up into the sky. So as it does, the amount of air inside the balloon won't change because I've sealed it off. I'm not blowing into it. But the pressure outside the balloon is going to change. So we start with an initial pressure inside that's equal to the pressure outside, which is why the size of the balloon is what it is. But as I let it go, it should do this. As I let it go, it should do this. Right. If you think about it, the pressure inside the balloon didn't change, but the pressure outside the balloon does. So when there's less pressure outside, the greater pressure inside is going to simply push the balloon outward and make it bigger. So when balloons go up in the air, they're going to grow and grow and grow until they eventually pop or reach a state where they've balanced the pressure inside and outside. And at that height, they may have reached an equilibrium in terms of buoyancy. So you could technically have a balloon hovering at a certain altitude, or it could get so high that it would actually pop. It all depends on what the balloon's made out of. So that answers our original question. All right, two ideas that we want to end with. We've talked about the first one. The density of the atmosphere decreases with altitude. Now we've added the idea that air pressure decreases with altitude. So again, these are something that you should definitely know. You can memorize it, or if you just think about it, it's pretty obvious. Okay, so as we already said, the answer to our original question is that the balloon should increase in volume or size as it rises into a lower pressure part of the atmosphere. All right, thanks guys. Stay tuned for part 2.